Hey, it's Jim, and this is FRM Part 1, Book 2, Quantitative Analysis, and the reading on machine learning methods. This is Part B, a continuation of Part A. Hopefully you watched that in the last day or two. You'll notice that we covered those first 4 learning objectives in Part A. Today we're going to cover the next 4 in Part B. Let me go ahead and make just a couple of comments. You should recall that we covered, in general, 3 types of machine learning. Remember, there was unsupervised and supervised and reinforced learning. We're going to continue on in that discussion. We're going to go down a couple of different paths. There's some similarities in the slide deck that we'll cover today, but there are a couple of interesting new points. Those of you who are super perceptive might say, hey, wait a minute, Jim, didn't you have longer hair yesterday when you made this video? And my wife gave me a free haircut last night. Boy, what a total waste of 10 seconds of your time that was. All right, so let's go ahead and continue our conversation on machine learning. Remember that we have these massive amounts of data. What did I say to you in Part A? We talked about LeBron James and Kareem Abdul-Jabbar. What did I say? 1 trillion data points. You know, of course, I made that number up. But you get the point that we're dealing with massive amounts of data. In my derivative securities class this morning, we had a conversation on option pricing, and we were talking about how interest rates affect option pricing. And one of my students asked me about the Fed and the Treasury and the budget here in the United States and the total amount of debt. And we had a conversation on, where are interest rates heading? And as I tell my students all the time, boy, if I knew that, I could be a billionaire by next week. But we have this tremendous data set. I mean, we could take a look at real interest rates, risk-free rates of interest. We could look at liquidity premiums and default risk premiums and maturity risk premiums. We could do this over the last 50 years. So think about all of those data points, just super publicly available data points that we could throw in to a machine learning algorithm and ask it to just do its stuff. And what did we do in Part A? We talked about clustering, we talked about reducing dimensions and principal component analysis. The idea behind all of this is that really we're trying to come up with a model that most accurately reflects reality. So we have some problems. In the second part of the reading, the authors discuss overfitting and underfitting, and these are exactly what you might think. Overfitting, what does that mean? You just try to stuff too many things into a bag. This is how my father used to explain traffic to me when I was complaining about traffic, and he would say, "Well, son, you can't fit 5 pounds of rocks in a 1 pound bag." And my dad was, super clever. Of course, he used a different word other than rocks, but, you kind of get the sense. Here's what the reading does for you, and I think this is a really fascinating example. Suppose that you program the machine learning to view the data as a polynomial. And I'm guessing that you remember that the simplest of all examples of polynomials, at least in the finance world, is computing the future value of savings. Let's suppose you want to figure out what your retirement value is going to be in 10 years. And suppose you plan on saving, just simply $100 every year for the next 10 years. How do you figure that out? Well, you could probably get out your financial calculator and you could do that really quickly. But if you wanted to do it the long way, you would take that $100 that you invest today times 1 plus some interest rate, say 8% or 5% or whatever it is, and you'd compound that out 10 periods. You'd raise it to the 10th, and then you do the next one. The one you save a year from now, that'll earn interest over 9 periods. So you say 1 plus 0.1, raise it to the 9th, and you add all those together. There's a polynomial. But what if your data set is just quadratic? Instead of being raised, x to the 10 and x to the 9 and all those things in a polynomial, so you get something that looks like that in a graph. It's just quadratic, and you get something that looks like that. So this is really the essence of overfitting. What does that second block point say? Too many model parameters, detail and noise, boy, cannot make reliable predictions, poor performance. So overfitting results in lots and lots of errors. But I like this last these last two circle points. We'll talk about training data and other kinds of data here in just a few minutes. But look, training data will have a low prediction error, but the new data will have a high prediction error when you have overfitting. Now, when you take a look at this data set, you're going to divide it into a training set and a validation set. And that training set, and this is important here because I think there's one question at the end of this reading, this will train the model that fits the parameters. Then the validation set will be used to evaluate. So remember those two words, training, of course, training, and then validation is to evaluate the model. So how do we solve this problem of overfitting? Well, I mean, exactly the commonsensical way. Decrease the complexity of the model, reducing features. Notice down at the bottom of the arrow point, we have these two words, regularization and early stopping. These are going to be super important topics that we do in the next reading. So I'll save that conversation for the next slide deck. But essentially, what you're going to do is you're going to take this model that is maybe a polynomial, but we only need quadratic. And so you take out a bunch of those features that simplify. So think of overfitting as need for simplification. Underfitting is, of course, just the opposite if the model is too simple. Since I brought this calculator up, let me do this here. You guys know, I take my glasses off so I can see across the top. Now I have the HP 10B2 Plus. I don't know where my 12C is. That's my favorite one. It's probably in the other room. So we have these 5 time value of money buttons. So we could punch those buttons and we could come up with a reasonable present value of a bond, and we could call that the bond price. So if we use that, we're going to get a bond price, but that model is so simple. You might remember in earlier recordings, and I say this to my students all the time, not in my basic finance class, but when I get my students into the upper level classes like investments or derivative securities, I tell them that that's a kindergarten model. We need a better model. We need a model that has an interest rate tree. Oh, you remember that interest rate tree where we have all of these branches and we have interest rate paths and we have to discount them based on which path we're taking. Recall that interest rate tree is super valuable for valuing bonds that have embedded options. Or we could use spot curves. We could use forward curves. We could use the swap curve. I mean, there are all different sorts of ways to come up with a more accurate present value or price of a bond. So if it's too simple, well, notice what the consequences are. Unable to capture underlying patterns, poor performance. Look at that third circle point. So that's an important one based on what we said on that previous slide. High prediction errors in both the training and the new data set. The reading does mention that sometimes we're expecting a relationship to be linear, but it's way more complex than that. So we need some kind of a curvy linear model. A linear model would be underfitting. That would be an example of it. Now, potential remedies for underfitting. So what did we do when we had overfitting? We simplified. So we're going to do just the opposite for underfitting. We're going to complexify. That's not a word, but you got the point. Increase the complexity of the model, add more features. And in the old time classical econometrics, that second circle point there, we would say something like add more independent variables. But remember, and I mentioned this in part A, that when we start adding more independent variables, we're necessarily going to get a high R squared, but then we might run into problems of multi-collinearity. Now remember, in machine learning, we can throw all of those classical econometrics assumptions aside, so we're not really worried about multi-collinearity. In fact, we would like to have those independent variables that we called them back in regular old stats, we'd like for them to have some kind of interaction. So that adds to the complexity of the model. And then we can increase the amount of training data. Now I love this next illustration here. Let me skip ahead just quickly. Oh man, look at that. That's a great curve. So what we're going to do is we're going to have a trade-off. I teach this to my children. I teach this to my students. Hopefully you've paid attention in my earlier recordings. We do this. Marginal costs and marginal benefits. This balancing act that we all learned back in our very first economics class. In fact, I had this economics as a junior in high school. Wow, that was a super long time ago. But what we're doing now is we're balancing the benefits of a simple model with the benefits of a complex model, and then we have to factor in all of the costs. So model complexity and prediction accuracy. I mean, what would we like to have? In an ideal world, we would have a perfect model that had a complexity that captured reality, which meant it had the ability to make accurate predictions. But what we learned, and what I learned even back in high school, is that when you make some kind of an estimate on a model, you're going to do it with error. And so in lots of models, statistics models, econometrics models, machine learning models, the goal is to minimize variance, right? We want no variability. We want to be able to say something like, if we work in a financial institution, I think I gave you this example in part A, when a customer walks into the bank and says, I'm here, I have a business, I need $1 million because I have a new product line and it's going to be super successful. Wouldn't it be awesome if you could just, use some superpowers like Batman or Superman or Wonder Woman or whoever it is, and you could just look or hear or whatever it is, and you could look into the soul and the core of this and the brain of this individual and say, yes, I think you're right. I think you will repay this loan and be successful. All right, so imagine that complexity, whatever it takes to be a superhero, although brooding seems to be one feature that we probably don't want to put into the machine learning model. So complexity, number of features, whether it's linear or nonlinear, what did I say earlier, polynomial or quadratic. All right, so let's go ahead and talk about the difference between variance and bias, right? Here's the example that I'm going to give you. Let's suppose that you have 4 darts in your hand and you're throwing them at a dart board, regular old dart board. And you throw 1, 2, 3, 4, and they hit the same spot, right? They're coagulated right at the same point on that dart board. Well, what do you have? If you look at that dart board, you're going to say, boy, there's tons of bias in there because those estimates or those outputs are all close together. So there's going to be high bias. There's going to be low standard deviation or low variance because they're all coagulated together. So we have low variance and high bias. Now let's take those out and let's throw 4 more times. So we do 1, 2, 3, 4, and they hit it 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. So now what do we have? Well, we have no bias there, right? We have no bias because you look at the board and they're all over the place. But what about the variance? You take your ruler out and you measure the distance between all those, and you got lots and lots of bias. So here's marginal cost and marginal benefit. So let's read those block points here. Bias occurs when a complex model is approximated with a simpler model. So that simple model means that when we throw the darts, they're all going to land around the same spot. Variance is how sensitive the model is to small fluctuations. Oh, this is so important. In fact, in my managerial finance class just today, we put together a capital budgeting problem where we estimated operating cash flows and free cash flows over just a 3-year window. It was a 3-year project. And what we did was we calculated net present value, and then I went back and said, well, let's suppose that the revenues are not these numbers. Let's suppose the revenues are a little bit higher. And then let's calculate net present value. And then let's suppose the revenues are a little bit lower. Let's recalculate net present value. So we have all of these potential net present values based on those inputs. Calculate the variance. If we don't make any changes, then the variance will be very, very low. So here's the graph. Notice model complexity going along the horizontal axis and error going up on the vertical axis. So what do we have? If we have a simple model, we have lots of bias. If we have a complex model, we have no bias because we're capturing all of those features. If we have a simple model, we're not going to have hardly any variance because we're eliminating all those other things that are out there. But if we have a complex model, we're probably going to have lots of variability. Oh, so what does that mean? If you take the green and you take the red and you add those two, you get total error. And so where are we right in the middle? There's this the black arrow, the smiley. Where do we want to be? We want to minimize that. So we're going to call that optimal model complexity. Now, after you guys watch this recording, I'm going to send you to the reading, and there's a question or two on this concept of optimal model complexity. And so all you're going to say is that, hey, marginal cost, marginal benefit, we want to trade off simplicity with complexity. And that should make perfect sense. Now, in part A, I mentioned just briefly this concept of data. Remember we had a slide where we had the data coming down from the bottom and then we did a whole bunch of other stuff. This was the whole flow chart of machine learning. And so that was kind of an introduction. So now we need to go and dive just a little bit more deeper into sample splitting and data preparation. So this is a specific learning objective. Wow, look at that first block point there. These algorithms are going to perform poorly when the variables used have different scales, right? Income and age, thousands and tens or hundreds of thousands, decades or days. I mean, they're all different sorts of scaling problems. So what did I tell you just briefly in part A? I mentioned standardization and normalization. And if you remember, I said something like, whenever statisticians standardize something, they just divide by the standard deviation. That's where the name comes from. Whenever they normalize something, they go ahead and they take the difference between the maximum and the minimum. So remember those differences from part A, and now we need to go and look at a little bit more of the math. So standardization, look down at the bottom. We're going to take the difference between each value, that's x sub I is 1 and 2 and 3 and 4, right? And then minus its mean, and then we divide by, well, there's the Greek lowercase sigma. So all we're doing is dividing by the standard deviation, and that is the process of standardization. Normalization, on the other hand, is we're going to do something similar. Here, let me go back real quick. Notice we're taking x sub I minus its mean value, but in the numerator, we're going to do something similar. We're going to start with that same x sub I, which is 1 and 2, right? And then we're going to subtract the minimum value. And then instead of dividing by the standard deviation, which, if you remember from our stats conversation, that standard deviation considers the entire horizontal axis, the entire distance from all of the potential variables. Remember that we talked about central limit theorem and that dude Chebyshev who taught us all about that. So back here in standardization, we need to worry about all that stuff. Here, we're just going to divide by the difference between the max and the min. So remember the difference between standardization and normalization, and then be able to answer a follow-up question here. Look down at the purple. If we're going to do standardization, the data must be normally distributed. That's probably super important. If we observe lots and lots of outliers, we're probably going to use standardization. Normalization is probably way more relevant and appropriate for distributions that are not known. So you see how cool this is based on what we talked about in part A, is that when you have this algorithm and machine learning, you don't have to worry about normal distributions and skewness and kurtosis and all that other kind of stuff. All right, so we got this massive data set, but it's not going to be perfect. It would be awesome if we could have a perfect data set. I'm not sure what that looks like. I know when I wrote my dissertation 100 years ago, I tried to have a perfect data set, but there's no way I was anywhere near perfection. So what do we have? Missing data. I think I've said this to you guys before, that I collected data on a bunch of firms that had what's known as a classified board. I also collected data on firms that had adopted poison pills. And so I did my best to go out and collect the entire sample of firms that had those two pieces in their corporate governance strategy. But there's no way that I didn't miss some data. In fact, my dissertation chairman said to me, "Hey, Jim, why don't you write a paragraph on your missing data?" And I was like, how am I supposed to write a paragraph if I don't know what's missing? And so I can't remember how we resolved it, but he signed at the very end. But here's a really good strategy, and I learned this from a really cool econometrics professor in college. You do your best to get missing data, but you can always replace a missing data. Now, this is important. If you know that it's missing. In my dissertation, I didn't know it was missing. But if you know it's missing, let's go back to that. Let's go back to my Part A example with LeBron and Kareem. Let's suppose that for LeBron, for some reason, there was a game on January 17th, 2008, where there's no data for NBA games. Somehow it just got wiped out. Now, of course, that's not really true, but that would be an example of missing data. So you can just replace that with the mean or the median, or maybe you could come up with some other idea. But that's a good strategy for handling missing data. Inconsistent recording. I know when we were all writing our dissertations and doing projects in graduate school, our professors kept saying, "You know what? You guys are going to the Wall Street Journal, you're going to the index, you're looking at all the microfiche." You guys even know what a microfiche is? In the old days, they used to put, hundreds of newspaper on this little thing, and you'd have to put it in and you'd have to view it. I mean, it was awful. So we were transposing data from these little small things, that are flashing at us, and we had to write it down, and then we had to go and put it into an Excel spreadsheet or put it in some kind of IBM code. And so, of course, we made mistakes all the time. Unwanted observations that are probably not relevant, duplicate observations, of course, and outliers. That makes sense. So let's continue this conversation on training, validation, and test data sets. I can imagine a really good example where you have a question stem where you're given something and the three choices are, is this training, validation, or test? So this slide will help you answer that question. Regularly, I ask the candidates to go ahead and get out their phones. I think this is probably a good one for you to take a picture. And then in your phone, you have a whole file of, hey, Jim told us to take a picture of these things. These are likely to show up on an exam. So look at the training data set, relationships between the input data and the desired output. And so we're going to go ahead and use this machine learning to make predictions. The validation set, we're going to evaluate that performance. And then the test data, this is like the out of sample data that we talked about back in classical econometrics. We're going to test it. Now, this is the big problem in machine learning, is that training data set typically takes up tons and tons of data, and there might not be too much left over for that test data set. So we need to make sure that we have some data left over. All right, so what do we want to do? Researchers can decide on how to subdivide into those three samples. So here's a common rule of thumb: 2/3 for training, the remaining third to be equally split between validation and testing. That's what I was saying here just a moment ago. Tons of data in training. Small training data set, that introduces bias. Small validation, that introduces variance in there. So this is a marginal cost, marginal benefit. So there could be a question on relating this stuff here back to our really cool illustration from a few moments ago. Yeah, how about handling the data if we have cross-sectional data? Now, when I wrote my dissertation on firms that had classified board provisions, my data set was cross-sectional because I had all these different firms. I can't remember how many there were, 150 or 200 of them or whatever the number was. And I collected data on those, let's say it's 200 firms, on all the different variables that I thought were relevant in terms of trying to figure out why and how and all that kind of stuff. So divide the data set randomly. I didn't do any of that stuff, but there's probably no natural order because you have firm 1 and firm 2 and firm 3. So just divide randomly. However, with time series, and remember how important this time series is, and we need to worry about these extra issues with time series because, boy, there might be multi-correlation, multi-collinearity. There might be, and there very likely will be serial correlation. So you need to make sure the time series is in chronological order. So start with training and then move through in the regular old chronology. So here are a couple of kind of concluding remarks that we've put together for cross-validation searches. You can do this when the overall data set is insufficient to divide into those 3 data sets. You can combine training and validation into one sample. What this is called is this k-fold cross-validation. So you kind of figure out what is the optimal number of Ks in there. This is Ks are, they don't stand for clusters like they did in part A, but they're kind of like that. You're trying to figure out what's the relevant number of Ks. But look down at the bottom there, K5 and K10 are commonly chosen for these cross-validation searches. And whenever I'm told that 5 and 10 or any numbers are commonly chosen, I always say, gosh, why not 4 and 9? Or why not 6 and 11? And so I'm always a questioner about things like that. But the reading says 5 and 10, so you can remember 5 and 10. Now, reinforced learning, we did this a little bit at the end of part A. And remember what I was saying to you, and I'll just go ahead and repeat it. I'll do it quickly here, is that you have an agent. And think of this agent as just in the middle of this machine learning algorithm, and you feed some data into the agent so the agent can process this. I think I used the simple example of a customer coming in for a loan, and what do we want to do? We want to lend customers money when we know they can repay, and we want to reject them when we know that they can't repay. So you have this agent, you feed this historical data or whatever data you come up with, and this agent then starts learning, right? It says, oh, this person here, this person repaid the loan, this person over here, this person defaulted, and they learn, so you have this learning. And then you go ahead and throw something else in, a dynamic change, like, oh, suppose inflation spikes, suppose energy price spike. And each time this agent makes the correct decision, you generate a reward. And then each time this agent makes an error, you penalize them. So here you go. Define the environment. You initialize the agent. That's exactly what I was talking about. And then you take an action. And the reading does have just a short paragraph in it about probabilities. They do talk about the difference between exploitation and exploration. This is probably a good multiple choice question. Exploitation is just going ahead and looking back and saying, you know what, I made this decision back then, I'm going to make that same decision today. Exploration is kind of moving out. Oh, I have a new scenario. Maybe it's high inflation, maybe it's low energy prices, whatever it is, and I'm going to try to make a new decision. So that exploration is a new decision, or a decision that hasn't been made under that given set of circumstances. So you update the agent. The agent, when the agent then explores, and you think about it, if the agent is out there exploring, it's more likely to make a mistake. So the punishment then has to be commensurate with the idea that, hey, the agent is taking a chance by exploring. That should make perfect sense. So what happens is that machine learning, based on the agent's decision, right, reinforced learning process, is that you can come up with this algorithm that optimizes the decision so that, and let me go back to my superhero example, this algorithm, when you look at this individual walking into your office, you can immediately say, oh yes, I approve, and no, I reject. And then if this algorithm is good, it will say something like, yes, I accept, I approve the loan, and I'm going to charge you this interest rate. Oh my gosh, so that's a dual decision, yes or no, and then if yes, what interest rate to charge. Oh my gosh, how many times have I said this to you before? Identify the risks, quantify the risk, manage the risk. Now the reading goes into this idea of reinforcement learning and the steps inside of the box and how the agent might make those decisions that will result in an optimal algorithm. And so the reading talks about Monte Carlo and temporal difference. Now we have equations here, and I'm going to just skip ahead just quickly here. We have a matrix, and then we have some math. Now, I want to emphasize to you that the questions at the end of this reading do not ask you to do this math, but I think when you work through the math, you're going to go ahead and say, hey, I'm glad I worked through the math. Maybe I'm glad I don't have to worry about it for the exam, but this will help you answer a question on the difference between Monte Carlo and temporal difference. So I want you to think about this before we look at this slide at all. I want you to think about how we're going to find ourselves in a different state. Now, a state is some unknown future condition. It might be a state of high inflation. It might be a state of surging stock prices. It might be a state of tremendous defaults in the financial service industry. And then we need to take an action. What is the action in these different states? And so we're going to have state 1, state 2, state 3, state 5, state 100, whatever it is. Now, of course, on the exam, if they give you up to state 100 on the exam, just pick B and move on with your life. So what we want to try to do is we want to try to maximize the expected value of the decision that we make. That decision that we make in the future, that's called an action. So notice there's some A's sprinkled throughout this slide deck. What do we know is the value of the firm? We know maximize shareholder wealth. We invest in projects that have positive net present values, but we have tons and tons of decisions that may or may not be reduced to investing in positive net present value projects. We just might have a quantitative decision like NPV, but we might have a qualitative decision. I tell my students this all the time, that good financial managers, good risk managers, they balance the science and technology behind all of this material with the artistry and the humanity of the human element in making these decisions. All right, so look at that. What is that? The 1, 2, 3, fourth bullet point. The estimated value of being in state S at any time. So whatever value we are, so there's the VS, it's going to be the maximum of some Q, and that is between the S and the A. So A is the action, S is the state, and we're going to base this on things like rewards and some constant, and we'll learn about this learning constant here in just a second. All right, so just think about this from a broad perspective. Is what we want to do is that when we find ourselves in state 1 or 2 or 3 or 10, we want to take the best action. And the action might be to accept or reject a loan, but it might be more than just a binomial choice. We may have 4 or 5 different choices, 4 or 5 different actions. So this matrix, now here, look, this matrix here is just pretty simple, but we might have a very complex matrix. So wherever we find ourselves in there, we want to make the best decision. All right. And that's really the difference between Monte Carlo and the TD method. All right. Now, go ahead and look down at the bottom gray box. There's an alpha in there. That's the learning rate. There's an R in there, and that is the reward. And that's the subsequent reward for making that decision. All right, so let's go ahead and kind of summarize all this stuff here in a table. So we have 3 states. And by the way, the reading really doesn't give us any idea about what these states are. So, I just kind of editorialized about, these different states that are possible. And then there are just 2 actions here. And so those Q values inside 0.3, 0.4, 0.5, 0.7, 0.6, 0.5, those are just those are just values at that particular node. Can I call it a node? For those of you who remember our conversations on interest rate trees, those are just those values. So the question then becomes, if we're reinforcement learning here, if we find ourselves in, let me just pick one here, state 2 and action 2, we're at 0.6. So we're going to get 0.6 out of that decision. Well, what this reinforcement learning model is going to do, it's going to say, let's have some learning that goes on and let's see how much better we can be. We want to improve our decision-making process over time. So we're going to do this in 2 ways. We're going to do Monte Carlo and the temporal difference method. All right, so you ready for this? So that first block point gives us our state. Our next trial, or action 2, is taken in state 3. So let's go back here. Action 2 is taken in state 3. So that's the bottom right. There's the 0.5. Okay. Now our reward is 1, and our alpha. Here, let me go back here. Where does it tell us? Oh, down the bottom left. So there, alpha is the learning rate. Now in the reading, the learning rate is given in the problem as 0.05. Here we've picked 0.075. And so think of if they give you an alpha on an exam, and it'll be somewhere around that value. All right. So what we're doing is we're asking ourselves how this Monte Carlo method would update our decision. Remember, we're trying to maximize the expected value. And so it's really just a matter of starting with our 0.5. So look at the second circle point there. We start with the 0.5, and we're going to add, how much did we learn? Well, our learning alpha, our constant there is 0.075, and all we're going to do is take the difference between 1 and the 0.5. 1 is that reward up there, and so you get 5375. So what we say is that, hey, we're at S3A2, we're at 0.5, but with reinforced learning, we're going to be able to add an extra, 0375. And then this Monte Carlo method of machine learning. Now, if we do the temporal difference method, we're going to ask ourselves the question, what if we have a different algorithm in here, and all we're going to do is we're going to take difference, right? So we're going to take the 0.5 plus, and we're going to start with that 0.75, and we're going to say 0.3 plus 0.6, and then we're going to minus the 0.5. And so there's the 0.3 and there's the 0.6. So we add those and we subtract those and we get 0.53. So in the temporal difference method, we're going from 0.5 to 0.53. We added 0.3 to that. Now, applications, I mentioned a couple of these things, but let's do some specifics that the reading mentions. Trading, detecting fraud, credit scoring, risk management, portfolio optimization. Of course, there's a good finance professor who focuses on investments and derivative securities. The key for me is that portfolio optimization. So you can use this reinforced learning. You can use the Monte Carlo. You can use the TD method to do what? To say, have this agent say, okay, I'm learning. And up pops a window, and the agent looks out at me from the computer and says, hey, you know what, Jim? It's time for you to replace Johnson & Johnson with Procter & Gamble. portfolio optimization, the agent is learning and learning. Remember, exploitation and exploration. The agent is learning. Remember on this previous one here, we're doing with the alpha and the reward. The agent is learning and learning. Think of how much value this adds on top of the Harry Markowitz efficient frontier that goes all the way back to 1952. Now, of course, for those of you in the commercial banking industry, that risk management is probably the most important column among these five, although probably detecting fraud is important and credit scoring as well. But risk management, we want to identify and manage those different types of risk. Imagine that a client comes into the office and you can just use your superpowers to identify liquidity risk and third-party risk and wrong way risk and all those other risks that we've talked about in all of these recordings. This machine learning can help accomplish those. All right, let's go to the last part of this reading, natural language processing. And this is something that me, and maybe you guys as well, as a finance PhD who loves math, who lives for math, might struggle with. But let me give you this example that I came up with as I was going through these last couple of pages of the reading. Let's suppose, for some crazy reason, that social media is increasing its chattering, am I using the right term there, surrounding Tiger Woods and the upcoming golf season. And let's suppose that we are the chief marketing strategist for a company like, well, what did I just say? Johnson & Johnson or Procter & Gamble or any company out there. And we're monitoring social media and we start seeing things out there that are like, boy, I hear Tiger's practicing down in his Florida home. I hear he's hitting his 5 iron, 270 yards, straight as an arrow. It's landing softly on the green. We see him putting in his backyard. He's making all of his putts. He's swinging as hard as he can so his back isn't hurting him, his leg isn't hurting him. He looks primed to return to his form of old. All right, so this is just social media chattering. And then we see somebody posts on Instagram, maybe another professional golfer says, boy, I was at Tiger's house last night and we were in his backyard and he holed out from 50 yards and he did a cartwheel and a flip. And I was like, dude, how could you have done that? You have a back, you have a knee. And Tiger says, man, my health, I feel like I'm 20 years old. All right, so hold off on this. So then you start reading in maybe the Wall Street Journal. Wall Street Journal has a sports section, maybe Sports Illustrated. Tiger is cautiously optimistic about the upcoming tournament. So you're this marketing strategist and you say, somewhere in there, you glean from the data that Tiger is pointing to the US Open. So you say, you know what? I'm going to go pick up the phone and call the TV station and I'm going to put tons of ads on the US Open because I think Tiger is going to win that or at least contend. And if he's in contention, what's going to happen? Everybody in the entire planet, what do we have? 8 billion people living on Earth now. They're all going to watch and they're going to see a commercial for brushing your teeth or a Q-tip and they're going to rush down to Walmart or Target and buy our product line. So that's what this natural language processing machine learning is, using natural language, whatever form that comes in. So data collection, so we can do this all over the place. Now, what that means is that when we collect these massive amounts of data, there's going to be tons and tons of noise in there, right? If we look at social media and we're trying to come up with a marketing strategy for the US Open, we don't really care about, what celebrity is posing over there on the beach, right? I don't look at those kind of things, but I'm aware they do that kind of stuff and everyone looks at it and says, oh, look at so-and-so's on the beach, right? So we need to process all of this data and get rid of the stuff that we don't want. So look at data pre-processing there. So we need to worry about formatting. We need to worry about cleanliness. We need to worry about stemming or tokenization. We'll talk about that in a minute. And we want to extract the important features, whatever that means. So model training is going to be based on those extracted features. What are some of those extracted features? Tiger Woods, cartwheel, 5-iron, putting, whatever those features are. We can do this just like we did before. We can have the beginning set, we can have the middle set, we can have the final set, right? The testing and the validation and the out of sample set. And then we can deploy that model and say something like, all right, let's go ahead and see if what we think is in this model is going to work. Now, of course, in my marketing strategy example, the success of this machine learning is really going to depend on Tiger and his ability to perform, right? But if we're talking about, well, let me just go back here. If we're talking about, now this slide, of course, was designed for reinforcement learning, but you could also say that this applies to this, this natural language, because we could put in there portfolio optimization. I mean, think about this now. If we know that Johnson & Johnson or Procter & Gamble is going to spend lots of money on marketing for the US Open because it expects Tiger to compete or to contend in that golf tournament, well, then it sounds an awful lot to us like we ought to add that stock to the portfolio today before all of that happens and before all of that information becomes publicly available. All right, so pre-processing, we need to get textual data more suitable for human consumption rather than computer processing. We need to remove numbers and HTML tags and punctuations. We need to pre-processing. We need to wrangle. This is called wrangling, which is tokenization. What we need to do is we need to separate a piece of text into smaller units, which means we're going to get rid of words that don't really matter, like was or it or is, like Tiger Woods will win or should contend or I think, you eliminate some of those words. Lowercasing, this is obvious, so you don't want the uppercase and the lowercase. You don't want stock, capital stock and lower stock, to be their separate tokens. And I've said this before, so you remove some of those words with no informational value. You can also do this process of stemming. So look at the example there. Earned, earnings, earning. They are all assigned a common stem. Lemmatization. These are words that are different words, but they have a common base form. The reading uses the example good, better, and best. Whenever you come across those, you just say it's all good. And then engrams, this is important if we have two words that need to go together, like strong earnings or poor earnings or low quality earnings, then we want to keep them together. So those are the engrams. So what did I say? Trading, risk management, news analysis, sentiment analysis, customer service, fraud, text classification. So essentially, that previous slide is appropriate here. And that takes us through part A and part B. Remember, at the end of part A, I asked you to go and look at those, 12 or 13 questions at the end of this reading. And I wanted you to do it just in like 10 or 12 minutes, just to casually go through and see which ones you can answer. But now I'm going to throw out that casuality. Is that a word? And I want you to go ahead and spend 30 minutes, give yourself 2 minutes for each of these questions. And I want you to work through them. And hopefully these last two recordings will help you get through those successfully. So thank you for watching, and have a great day, and good luck studying.